I think, Dr. Anand, we can start.
Yeah, with your kind
5 more.
permission, Mr. Stephen, should we go ahead?
Yeah, sure. Shall I share my screen?
Just a minute, sir. Formally, I will formally introduce you to the audience
Okay,
and
okay,
then we'll.
thanks.
Yeah. Good morning, everyone present here. This is Dr. Arun Prakash Agrawal, your host. And this is the third day of this international FDP, which is the fourth one in the series, aimed on recent advances in computer science and allied domains. And this is the fifth technical session of this FDP. And today we have with us Mr. Mary Stephen Leo, who is the Director of Data Science, APEC Edelman Data and Intelligence Group, Singapore. Let me take this opportunity now to formally introduce him to the audience. As I told you, the Mary Stephen Leo, his domain of interest is natural language processing, computer vision, AWS, neural search, MLOps, and data-centric AI. At Edelman, he manages a team of data scientists to research, architect, develop, and scale cutting-edge machine learning products from concept to production using cloud technology. Under his leadership at Edelman, the team has grown by 3 times and covers the entire end-to-end product development lifecycle. As a leader, he believes in nurturing a research-focused organization that researches the current state of the art while solving problems and makes solid decisions backed by the data and experimentation. He has almost 12 years of experience in generating measurable value from data assets while managing teams of data scientists and engineers. He also keeps writing monthly blog posts on highly technical topics on Medium, which is, I think, every one of us is aware of. He achieved top writer in artificial intelligence by 3x on Medium with over 716 followers and which is continuously growing. He has also published in Association of Computational Linguistics in July 2020 and has one patent to his credit. He has also delivered several keynote talks at various international conferences of repute. And very recently, he has invented StripNet, which stands for Semantic Similarity of Scientific Papers Network, which help us out in classifying the papers that we read within a specified period of time, might be 1 year, might be 2 years, might be 6 months. With these words, may I now request Mr. Stephen to kindly take over and address the audience. Over to you, sir.
Thank you. Thank you for the very nice introduction, Doctor. So
My
let me
pleasure, sir.
share my screen. Okay, good morning to all the professors and attendees. Thank you very much for inviting me to give this talk. So today's talk is called No Training Data, No Problem, Weak Supervision to the Rescue. It's mainly going to be focused on natural language processing. And the whole talk is based on my Medium blog post. So you can access that blog post by scanning this QR code. And at the end of that blog post, there is a link to the slides as well. So if you need the slides, you can take it from there. Or we can connect on LinkedIn as well. So just drop me a connection request. I will connect with you. Okay, since Dr. Arun has given a good introduction about myself, I will skip this slide. Right, so let's jump into the agenda for today's talk. We'll first discuss about some of the challenges around contemporary machine learning, specifically around the need for massive labeled datasets. We'll then discuss the concept of weak supervision and how it alleviates this problem. Then I'll introduce a couple of very, very powerful open source weak supervision frameworks that you can use to implement weak supervision on your problems. They are all backed by solid research and they have papers that have been published very recently. All of this work is things that we have tested out at Edelman and they work really well in the industry. So I'm very confident that it will work on your problems as well. So finally, we'll wrap up the talk with a conclusion and the direction I am seeing this technology moving in the coming years as some inspiration for you guys. Okay, so first, one of the big challenges that real world machine learning models face today is the need for massive amounts of manually labeled training data sets, right? So for example, the famous ImageNet dataset that pretty much every computer vision model is trained on these days, it has about 14 million manually annotated images, right? So 14 million is 140 lakhs, I think like 1 crore 40 lakhs. So with the advent of transfer learning techniques, this situation has improved drastically. But yeah, we do not need millions of label data anymore. But most models, they still require at least a few hundreds, or more commonly, at least a few thousands of high quality hand labels to fine tune. For example, if you're doing natural language processing, then to fine tune BERT based models, you need at least a few thousands of high quality label datasets. It's in the industry, it's not uncommon that we collect somewhere in the range of 50 to 60,000 labels for training our models today. So as you might have experienced in the past, if you have worked with these kind of large models, or as you might imagine, collecting so much manual labels is costly. Number one, because most of the teams in the industry, we don't do the labels in-house. We hire some external vendor. We outsource the labeling to an external vendor, or we outsource it to crowd workers like Amazon's AWS Mechanical Turk. So all of this, we need to pay money to the external labelers to label the data for us. It's also definitely time consuming. You can imagine reading through all the data and labeling it one by one is really a labor intensive and time consuming process. And one of the issues with human labeling is that human beings are inherently biased based on our experience in the past, and also error prone, right? Because natural language, especially for NLP, natural language is very subjective. The same word can have multiple meanings in different contexts. So when these kind of subjective things happens, the way different people perceive the same sentence might be different and ambiguous. And finally, which is a very big problem for domains where the knowledge requires tremendous domain knowledge, right? Before you label, you need a lot of domain knowledge. For example, if you're labeling X-rays to find out if there is a chest tumor or tuberculosis in the chest. So this kind of how to read a chest X-ray, you need the domain knowledge of radiology before you can label that data. It's very difficult to get labels for these kind of domains because the subject matter experts, basically the guys who have the knowledge uh, to label this data for you, they have to run their business. They have to run the business, right? And they do not have time to actually sit down and label data for our models. So it's a chicken and egg situation. Like you don't have data to train your models, and the people who can label the data for you, they are too busy to label data for you. So with all those problems being said, uh, it is a fact that unlabeled data is vastly abundant, right? We have tons and tons of unlabeled data on the internet, and through any company always produces a lot of data. We just don't have the labels on that unlabeled data to train our machine learning models. So most companies, most organizations that I have worked at so far, they have a lot of domain knowledge locked up in people's brains, right? So as tribal knowledge, like as you work in a company for more and more years, you will start to pick up some signals that can indicate how things will happen. So that is tribal knowledge. Or you might have some heuristical rules, right? If situation A happens, then we need to do task A or task B. So these kind of heuristical rules, some kind of search queries, like if you've worked with Elasticsearch before, there's a lot of databases that can be queried in either a SQL query language or in a Elasticsearch query language. So all of this might be rules that people have inherently over time built up using their knowledge of the problem they are solving. But unfortunately, all this domain knowledge is not being used by most of the machine learning models today, right? So we ignore all the wealth of information locked up in people's brains. And instead, for machine learning, we tend to rely on the labels from crowd workers or the labels from non-experts. So we start to ask ourselves these questions at Edelman. The first question is, and Edelman is another typical company which has a lot of domain knowledge locked up in people's brains, and we're trying to unlock that knowledge using machine learning. So these are the questions that my team asked ourselves. Can we leverage the wealth of the domain knowledge in our organizations and use that domain knowledge to label data? And if we can do so in a programmatic fashion, we can run this labeling process on the entire corpus of unlabeled data. Because it's programmatic, you can run it automatically on the whole corpus of unlabeled data, even if the unlabeled data has millions of rows, right? So once it's a program, you can run it on millions, billions of rows of data. And at the same time, because the labels are generated from the knowledge of our subject matter experts, our domain knowledge of our experts, these labels would have a higher quality than the labels that are generated by just hiring some intern or hiring some external person who does not know your business very well. So in essence, this is what weak supervision allows us to do. So let's talk about weak supervision more formally and why weak supervision is becoming a hot trend in the industry right now. So there is a paradigm shift happening in the AI industry these days, and that's the shift towards data-centric AI. Weak supervision is just one of the ways to actually implement a data-centric AI policy at your company. Right. So if you guys are familiar with Andrew Ng, he's a very popular researcher in the AI field, and he defines data-centric AI as a discipline of systematically engineering the data used to build AI systems. So what does this mean to us? So throughout the 2010s, right, the past 10 years, there has been a very large focus on the AI and ML models themselves. So we focus a lot on the models. We keep our training data, we collect the training data once and then keep the training data fixed. And then we iterate by trying different models, different hyperparameters, etc. And the goal is with each iteration of a different model with a different hyperparameter, we try to get better accuracies. In general, through my experience in the industry, we see like plus or minus 1% change in the accuracy when we change hyperparameters, change models. We don't see like a very huge difference with respect to some baseline model that we build. However, in the 2020s, basically the current decade that we are in, the advent of large scale models like BERT and GPT-3, like these models, they encode a lot of knowledge into the models. So the models themselves are becoming pretty much standardized and commoditized. There's not much variation you can try beyond BERT, right? There are many variations of BERT, and you're pretty much fixed, you're pretty much zoomed into this model architecture. So the way that we can get better performance of the final predictions that we are trying to do is to keep our model as standardized and fix our model and then iterate over the training data. So in real world problems, the way I see it is when we change the training data to improve the quality of the training data, we can get changes in accuracy of our predictions by one order of magnitude more than any improvement that we can get by just changing the model itself. So changing the data itself can give us a bigger change, a bigger improvement in the accuracy. So it's because of this kind of situation that we are in right now. We have these very large pre-trained models from companies like Google, Facebook. We can keep the models fixed and then iterate over the training data. So this is called data-centric AI, and it is expected that throughout the 2020s, we are going to see a lot more focus on data-centric AI approaches where we are iterating on versions of the data to improve the performance of our predictions rather than iterating over the models themselves. Okay, so as I mentioned, weak supervision is one of the ways to implement a data-centric AI philosophy, a way to iterate on your data set continuously to keep improving your model performance. And one of the big companies in this area right now is called Snorkel AI. They are the Stanford University research group that released the open source Snorkel library. And that's the library pretty much we're going to be talking about in the subsequent slides. They are currently a $1 billion company. So I believe moving forward in the upcoming years, we'll see more and more investments in this area. Right. So it might still be a bit not clear as to what weak supervision is. So I hope this slide will make it much more clearer. If I were to explain weak supervision on one slide, it is this. Today's machine learning models, basically the red box over here, we ignore or have a very less input from the subject matter domain experts, but we place a lot of importance to the knowledge of non-experts. So this is how we are building our machine learning models today. We don't consider the domain knowledge of experts as much as we consider the knowledge from our non-experts who are labeling the data for us. But with weak supervision, basically the green box over here, we don't leave any information on the table. We can use both the domain knowledge of our experts and the knowledge from non-experts to build our machine learning models. So in essence, we use programmatic labeling sources to reduce the efforts of manual labeling, while at the same time, we are embedding the knowledge of our domain subject matter experts into our machine learning models. So that is weak supervision in one slide. So from here on, the slides are going to be a little bit more technical. So I'll explain how exactly we are going to go, how exactly we are doing this in code. Okay, so this picture is a snapshot of the actual steps involved in using weak supervision for your problems. So if you're going to build a weak supervision system for solving your machine learning problem, you will have all these steps inside. So in general, during the model training phase, so we have two phases, right? We have the model training phase and then we have the model inference phase. So during the model training phase, there are 4 steps. So we'll talk about each steps in very much details in the subsequent slides. But at the very high level, the first step is we need to get our subject matter experts to describe their knowledge as rules that we can code up using Python functions, right? So we're going to write some labeling functions, which is the knowledge of our subject matter experts transformed into Python functions. The second step is we take all these labeling functions and we combine their outputs using what is called a label model. The third step is we use the combined outputs out of the label model as our training data to train a downstream end model. We can use this training data to fine tune any model like BERT and Roberta and so on. And the final step is to iterate. So we look at the prediction accuracy, then we find out which of the functions are not performing well. We go back to the subject matter experts and say, can you fine tune how this function has been written to be more accurate? And then we iterate over it. So this is a very iterative process. We need to write functions, combine them, train the model, and then based on the model predictions, go back to iterate and fine tune the functions. So that is during model training phase. During model inference phase, we actually don't need any of this. We only need the end model. So we can leave out everything else and just take the end model to make predictions. So the end model by itself is sufficient. And because of this, it is no different from any other normal machine learning model. Like if you're using BERT for making predictions, like sentiment analysis, you're using BERT to make predictions, this will still be a BERT model that you're using for predictions. So during model inference, there's actually no difference to us. So let's take a look at all of these steps in very much details now. The first step is the creation of labeling functions. And basically, this is the step that is encoding the knowledge of our domain experts into Python functions. So we are calling these Python functions as labeling functions. This is the term used by the Snorkel library. A labeling function is basically any Python function that takes in one data point as input and returns either one label as output or abstains from labeling. Basically, if it does not have enough information, the function should just abstain from labeling. It says, I don't have information, so I don't want to label something wrong. So for example, if you want to build a model to detect spam YouTube comments. One of the labeling function can be as described here. If the phrase HTTP is present in the comment text, then we call it a spam. If not, we say that we don't have enough information to make a conclusion whether this comment is a spam or not a spam, and hence we abstain from giving any label, right? So labeling functions can be as simple as this. We just need to add this decorator, which is imported from the Snorkel library. So basically, labeling functions can be anything. Whatever you can write as a Python function can be a labeling function. You can use keywords as shown here, the keyword HTTP. You can use heuristic rules, if else. You can use queries. You can even use the outputs of other models. For example, for natural language processing, there are zero-shot models and there are few-shot models like GPT-3, but you can use the outputs of these models as one of the labeling function as well. And one of the very cool things that we were able to do at Edelman is we could use external databases. For example, for named entity recognition problems, you can use some external database like DBpedia, or you can use Wikidata for named entity resolution and so on. Like you can use an external database as a way to create a labeling function for yourself. So as shown here, creating labeling functions is super easy with Snorkel. You just need to import and add this decorator to any Python function, and it will become a labeling function. And the labeling functions are absolutely not expected to be perfect. In fact, it is expected that the labeling functions will be noisy and will be far from accurate, but it's okay because in the subsequent steps, we have ways to handle that noise. So this is the first step involved in weak supervision. We convert the domain knowledge of our experts into Python labeling functions. So in the second step, right now you have a bunch of labeling functions that have encoded the domain knowledge of your experts. So the next step is we want to combine all of these outputs by using the label model. Why this is important is as follows. If you have n labeling functions, then each row of data would get n labels, right? So if you look here, I have 5 rows of data, and let's say I have 5 labeling functions, then each row can get a maximum of 5 labels. So some labels will be spam, some will be abstain, some will be ham. But to train our model, we only need 1 label per row, right? We cannot train a model with n labels per row. So as you might expect, combining n labels per row into 1 label per row, the easiest way to do this is by just taking a majority vote, right? If majority of the labeling functions are labeling this row as spam, then we consider that the true label for this row is spam. So it is definitely one of the options available, the simplest options available, but the Snorkel paper and the Snorkel library implements some even better ways using some matrix mathematics. We'll talk about this when we get to Snorkel later. The really cool thing to take note of is that coming up, like determining the one single label for the entire row does not require the ground truth data at all. So you don't need to know the exact label for this row. You can still approximately find out what is the label for this row by using some matrix mathematics. So that is what the whole Snorkel paper and the Snorkel library is about. But in practice, doing all of this, it's a bit scary that you don't have any reference of the actual label, the actual reference. So I always recommend to collect a small, maybe 100 rows of high quality hand labels. Just you can, as a data scientist, you can sit yourself and label maybe 100 rows of data so that you can convince yourself or you can convince your boss and your stakeholders that you're doing the right thing and you're not doing something that is totally wrong. So this sample set of 100 rows is really small that you can also ask your domain experts to label that for you. And yeah, just don't ask them to label 1,000 rows of data and then they probably won't label anything for you. Right. So in the second step, we have taken all the outputs from the individual functions that we have, and combined it into just one label for each row. That is the job of this label model. Okay, the third step, now that we have one label per row as the output of our label model, this can basically be treated as our training data. So we have a row of features and we have one label that we want to predict. So we can use this training data to fine tune a pre-trained end model. And yeah, basically we can use this training data is called as weak labels because they are generated using the labeling functions rather than actually being generated by somebody who's labeling each row. So we call these weak labels. We can use it as the training data to fine tune a downstream pre-trained model. And the goal of fine tuning these pre-trained models is to generalize beyond what the weak labels are capturing. We need, basically transfer learning is very important to weak supervision because we need to use pre-trained models like BERT or Robeta. And these large pre-trained models, they have been trained on the entire text of the internet. They've been trained on Wikipedia, right? So they have they have a tremendous understanding of our language, of our natural world. So by just fine tuning these models using the weak labels, we are able to leverage the knowledge that these models already have about our world and just nudging it slightly towards the domain that we are trying to solve. So we are not going to completely train the model from scratch. These weak labels are not sufficient to train the models completely from scratch, but we can leverage the knowledge that these big models like BERT already have about our natural world and just move it closer towards the domain we're trying to solve by fine tuning it on our weak labels. And since our labeling functions are programmatic, they are basically Python functions, right? So we can run the labeling functions on our entire unlabeled corpus so that we can generate millions of rows of data and use these millions of rows as the training data set. You can never get so, like in a normal company, you can never get a million rows of hand labeled data. Even companies like Google and like those big technology companies, they need to spend a lot of money and time to generate this volume of labeled data sets. So weak supervision is a way for smaller organizations and research organizations to generate a large volume of training data set by leveraging the domain knowledge of your experts. So again, to reinforce what we have done so far is to encode the domain knowledge of our experts to create a massive training data set completely programmatically, and then fine tune our model based on that massive data set. So basically, it's a win-win situation. You have created a large training data set, and you've also incorporated the domain knowledge of your subject matter experts. Right. So with that, we come to the end of model training. Let's look at model inference. So during model inference, this is a pretty straightforward process. We only need our end model, and we can treat it as any other BERT model. You just pass it your input text and you get your predictions as output. But it's not wise to throw away all the work that you have done so far, basically your labeling functions and your label model. Don't throw them away, because you can reuse them for model retraining at a regular cadence or for model monitoring for performance degradation over time. So this is, sorry about that. So this is the realm of ML ops. Now, like, how do you monitor that your model is giving you good predictions over time and it's not drifting? So having these labeling functions, having this label model gives you that continuous signal that you can continue to monitor your performance of your model over time, because the labels are generated completely programmatically. You don't need to keep asking someone to generate labels for you before you can check the performance of your models. So this is another benefit of using weak supervision, that you can continuously monitor the performance of your model. Okay, so with that in-depth understanding of weak supervision conceptually, let's now spend some time to talk about a few very powerful frameworks you can use to implement weak supervision on your data, right? So I'm taking this picture from a paper that was published late last year. The paper is called Wrench, a comprehensive benchmark for weak supervision. Basically, the authors have tested out many different methods of label models and many different, basically they tested a few different models of label model, a few different methods for the end model. And they ran the test on many different standard benchmarking data sets as shown here. Majority are natural language processing. Those in star are computer vision datasets. So you can see that we can use weak supervision, both natural language processing as well as computer vision, as long as you have a good pre-trained model that you can fine tune. So the red column over here is the baseline performance of a fully supervised model. Because these datasets are standard benchmarking datasets, they have a standard training split and a standard validation split. So if you just treat this as a standard supervised machine learning model, you can use the training dataset to train the model and then test it on the test dataset. So these numbers here are just treating it as a fully supervised approach. This is how you would normally build your models. And yeah, this would act as the benchmark that we are going to compare our weak supervision approaches to. Then you see there is top 1, top 2, and top 3. This top 1 is the best performing weak supervision approach for each dataset. So for the IMDb dataset, the top 1 performing weak supervision approach was this RC for end model and metal for label model. Top 2 was RC for end model, FS for label model. And the definition of RC, FS, all that is over here. So FS is flying squid, RC is cosine rho beta. And the paper goes into much detail about how they set up the experiments and all this. Right, top 2 is the second best performing weak supervision approach. Top 3 is the third best performing weak supervision approach, and so on. Let's just focus on the top 1 here because that is more than sufficient for us. The blue column is the performance of a fully weak supervision approach. Basically, we do not use the training data at all, but based on our knowledge of the task, the authors are writing labeling functions, then combining it using the label model described here, and then using the output of the label model to train the end model described here. So completely weak supervised, they are not using any labels at all. So right off the bat, you can see that despite not using any label data to train, the weak supervision models, and of course the caveat here is that you need to write the appropriate labeling functions. These weak supervision models can achieve pretty close and sometimes even better performance. Like if you see this model, the performance of weak supervision can be even better than a fully supervised approach. So with that promising results, let's take a look closely into what are the end model and the label models that are giving us the best results. So if we look at the end model, consistently you see that RC and BC are showing up in the top 1. And RC and BC are basically based on a paper called cosine, which we will talk about in the, I think the next slide, we'll talk about it shortly. So RC stands for cosine rho beta and BC stands for cosine BERT. So rho beta and BERT are the pre-trained model that they're using. Cosine is the approach to train this model in a noise-aware situation. Right, we'll talk about that in detail shortly. So for our problems, it is you cannot go wrong by directly choosing cosine rho beta or cosine BERT for the end model. While for the label model itself, there isn't a clear convergence to one specific method, and depending on the data set, different methods are showing up as the best method in the top 1. So it's wise to test out a few different methods before choosing one. But the Snorkel library implements a few of these different methods. It implements the metal, it implements majority voting, and it implements data programming. So the Snorkel library is a good place to start because it implements majority of the methods that are showing up here in the top 1. Right. So one thing to really bring home the point is that despite not using any label data, the weak supervised models with appropriate labeling functions can achieve pretty comparable and sometimes even better results than a fully supervised model. Right. So let's talk about the label model first, and I'll talk about Snorkel, how Snorkel is working under the hood. So Snorkel is a Python library, an open source Python library developed by the Stanford research group that published the Metal paper, that they published the Snorkel paper. And yeah, to recollect, at the end of our labeling function stage, each row of data has one label for each labeling function, as shown here. If I have 5 labeling functions, each row has one label for each labeling function. So Snorkel, the goal of Snorkel is to use this entire table to construct a correlation table as shown here. So in this correlation table, each row and each column is one labeling function. So lambda1 is labeling function 1, lambda2 is labeling function 2. So they construct a correlation table as shown here. And the last column is basically the correlation to the actual label that a human would have labeled for this row. We do not know this, right? We do not know what is the actual label that a human would label for this row. And that is what we are trying to find out. We know everything in this green box because we have all these values. We can find the correlation between labeling function 1 and labeling function 2. We can find the correlation coefficient and fill up this box. And basically everything in the green can be filled up by just the labels that we have from all our labeling functions. And once we have constructed this kind of a table in which the green box is known, and we want to find out the red box, this is something that can be calculated using a matrix completion approach using stochastic gradient descent. So we uh, impute random values for each of this and then solve the equation for the matrix completion. If the error is high, then we change the values here towards the direction of reducing the error, like basic stochastic gradient descent, and continue to solve it iteration over iteration. So the good news for us is that all of this mathematics and this stochastic gradient descent process is being done under the hood by Snorkel. It's just one line of code that we need to call after we define all our labeling functions. We just need to call one line of code, and Snorkel will generate all of this under the hood that abstracts away all the complexity from us. And in the end, Snorkel will give us something that looks like this, a summary table, which shows us like how many rows. Basically, it gives us like 3 columns. The first column, coverage, tells me that how many percentage of rows labeling function 1 is not abstaining. So 60% of the rows labeling function 1 is not abstaining. And overlap says how many percent of the rows labeling function 1 overlaps with some other labeling function here. So looking at it, labeling function 1 has overlap with 100% of labeling function 1's labels are overlapping with some other labeling function. That's why it's 1. And conflicts are the percentage of rows in which labeling function 1 has a conflict with some other labeling function. So you see here, labeling function 1 is labeling as spam, but labeling function 2 is labeling as ham. So all of this information is getting used to complete this matrix and estimate what is the correlation between each labeling function to the unknown actual label for that row. And once this is run, we can decide whether we want to remove any labeling function. For example, if I see labeling function 5, if, for example, I see 100% of labeling function 5 is conflicting with all the other labeling functions, then maybe labeling function 5 is a noisy labeling function and we want to drop it. So we can do that before we call another line of code to generate this output table, which is the single combined label per row. So in essence, using the Snorkel library with about 2 lines of code, we can go from the output of our labeling functions, which is a table like this, to the output of our label model, which is just one label for each row of data, right? And once you have this table, this is basically what all of our machine learning models expect. I have the row, which is the features for me for natural language processing. This is the text, and this is the label for that text, right? Once I have this table, I can feed this to any downstream model and fine tune it. Right. So Snorkel, we just discussed about using Snorkel for our label model, which is combining the individual labeling functions into a single label per row. The next step is to use cosine for training, basically to fine tune the downstream end model. So cosine is actually a very new paper, and it was just published last year in ACL. It has a few steps and it is complicated. So let me try to explain it as intuitively as possible. The first step in cosine is to use all the weak labels that we just generated using the Snorkel library. So Snorkel library is giving me one label per row of data. Use these weak labels to fine tune a normal pre-trained BERT or Roberta model. So I just download a BERT model from Hugging Face, use the weak labels that Snorkel has generated, and fine tune it for maybe like 5 epochs, right? Just for a small number of epochs. And this is called the initialization step. So I'm initializing this pre-trained BERT model using the weak labels that Snorkel has generated. In the second step, we use the fine-tuned model to make predictions on the entire dataset. So remember, Snorkel, like the labeling, the whole premise of a labeling function is it will only give a label if it is confident of making a prediction. If it is like, depends on how we write the labeling function. If we are not confident or we don't have enough information, we can abstain from giving any label output. So there would be some rows in which all the labeling functions have abstained. So using this BERT model that we just fine-tuned in the first step, we run predictions of all the rows of data, those rows that have output from Snorkel and those rows that in which Snorkel is abstaining, right? We just run all of these samples through the BERT model and make predictions to see what is the class for each of this row. Right. After we make the predictions, one important thing that we need to do, and this is how we are handling the noise, is that those predictions in which the prediction probability is high, we are giving it a high weight. And those predictions in which the prediction probability is low, we are giving it a lower weightage. So this is a way for us to handle noise. In the third step, we take all those rows that have a high confidence in the prediction, and we calculate both a classification loss as well as a contrastive loss on those samples, right? We only take those samples in which the model has a high prediction probability, and we calculate classification loss and contrastive loss. So the idea here is that those texts that are similar in meaning should be closer together in vector space. And this is another way to denoise the situation, denoise our labels by looking at it from a vector space perspective. So contrastive loss is very popular in self-supervised learning. It's a way to ensure that similar texts are grouped closer together in vector space. And we're using that as one of the loss mechanism. And finally, the last step is that we add some regularization so that those rows that have a wrong prediction, but they're having very high confidence, very high prediction probability. So those rows with wrong prediction, but very high confidence, those rows needs to be penalized. And that is where this confidence regularization comes into play. So all of this is basically trying to minimize the noise from our labels, because weak supervision gives noisy labels. We want to reduce the amount of noise. So the final loss of the cosine model is basically the summation of all these three losses: the classification loss, contrastive loss, and the confidence regularizer loss. So we continue to fine tune this BERT model using this compound loss, the summation of these three losses, until the model converges. And once the model converges, we can then just take this BERT model as our final model that we can use for inference. So we can drop out everything else and just use the model finally. So it's definitely more complex than just fine-tuning a model directly based on the output of the Snorkel library. But doing it in this approach helps to reduce some noise and gives really good results in practice. Right. So that was the label model and the N model that are the most promising that I'm seeing right now. But however, despite all this, in real world testing, we notice that the performance of the N model can vary a lot depending on the quality of the labeling functions. So in essence, the uh, the mathematics involved in the snorkel label model has a strong assumption that each labeling function is truthfully tackling one aspect of the problem statement. So if we have some malicious labeling function or some labeling function that is totally wrong, it can poison the calculation of the label model. And this poisoning can lead to poorer results. So we need to be really careful about how we are selecting which labeling functions are being fed into the snorkel label model. But the issue here is that we do not know in advance which labeling functions are good and which labeling functions are bad. So at Edelman, we implemented a very simple pipeline that looks like this. We call it a heuristic labeling function subset selection. Basically, from the subject matter experts, we collect a bunch of labeling functions, and this can be like hundreds or several hundreds of labeling functions. And then we send it through, we send different subsets of these labeling functions through this entire pipeline. So we select maybe labeling function 1, 2, and 3, and then measure the performance of our N model. Then we select labeling function 1, 2, 3, and 4, and then measure the performance of our N model. So you can think of it as a very iterative process. We select labeling functions, we drop labeling functions, and we try to find the subset of labeling functions that give us the best performance of our N model on a small hand label data set. Like you just need 100 rows of hand labels to make this kind of a fine tuning. So it's very similar to hyperparameter tuning. We keep iterating until we find a subset that gives us the best performance. And from our practical experience, we found that this kind of a iterative approach can give us really good results and very high quality models. Right, with that, I've come to the end of this presentation. Let me take about 3 more slides to wrap up. So in conclusion, there is a paradigm shift happening towards data-centric AI, and that's already happening right now. Weak supervision is a great way to implement data-centric AI for your projects. There are 4 steps involved in building a weak supervision model. First, we need to encode the domain knowledge of our experts into Python labeling functions. We can then combine those labeling functions using the Snorkel label model. We then use the labels from the label model to train a downstream N model such as Roberta or BERT, and specifically using the cosine approach of fine tuning. And finally, we need to iterate, right, with different combinations of labeling functions and different, even fine tune the existing labeling functions until you can get good results on a small hand label dataset. In terms of open source frameworks available right now that can help us to implement this, Wrench, the paper that I initially introduced, has a lot of code implemented to run benchmarking. So if you want to run benchmark across multiple different approaches, you can leverage the implementations from Wrench. Snorkel is pretty much the best way I have found out there for implementing the label model. And cosine is the best method I have found for implementing the N model. For labeling function selection, you can write a in-house heuristic labeling function selection pipeline. Just use normal leave dropout, or you can even use any kind of Bayesian optimization if you need. And as with anything in data science, these are all great starting points, but you'll definitely need to experiment on your own data to choose the best ones. In terms of future directions, I'm currently seeing more research papers on a concept known as extreme weak supervision, which is trying to generate the labeling functions itself automatically. Right. So right now, the biggest bottleneck for weak supervision is actually to generate the labeling functions. You need to ask your domain experts on what kind of labeling functions you can use for your problem. So if you can even automate that labeling function itself automatically, then that would give you another level of automation to like make the whole thing super automated. So there are a couple of papers published, as I've mentioned here, so definitely take a look at them. We haven't experimented on them much in Edelman, so cannot say how good they are, but yeah, it is a direction I'm seeing happening right now in the research in the research field. And there is also a rise in UI-based tools for labeling function. So if you think about it, the best people to create labeling function are the domain experts, right? And these domain experts may not be coding experts. So they may not be able to translate their knowledge into a Python function. So these UI-based tools, such as the open source tool called Rubrics and the commercial tool called Snorkel Flow, basically this was developed by the Snorkel AI company. So these UI based tools come in really handy to like just open up an interface to your domain experts and say, here's the data. Can you help to figure out what are the rules that can encode your knowledge? So yeah, I do see a lot of UI based tools coming up as well. And I think it's a good place for beginners to start off with is Rubrics. Like you can play around with it and see how the whole process works end to end. Right, and the last slide is links to more resources. So yeah, as I mentioned, this talk is based out of a Medium blog post. So the link to the blog post is here. The Snorkel website has a lot of tutorials if you're interested in implementing some Snorkel-based, if you're interested in implementing Snorkel on your projects, I definitely recommend to check out their website and the tutorials they have there. The data-centric AI website also has a lot of resources, and there is an O'Reilly book. I would highly recommend if you are able to read this book. It goes into details of weak supervision, not just for natural language processing, but also for computer vision problems, right? So it can show you how you can apply weak supervision even for computer vision. Okay, with that, I come to the end of my presentation. Thank you so much for listening, and I can take any questions now.
Thank you so much, sir. And I can see one question asked by Udaini Chandana, which is there in the chat window. She is interested in knowing, can we use this weak supervision model for medical image processing? Is it advisable?
Yes, absolutely. So one of the big, among other benefits, one of the big benefits of weak supervision is its explainability part. So since you are writing labeling functions to actually detect something on a medical image. So for example, if you're trying to detect TB in a chest X-ray, right? So you are writing labeling functions, and those labeling functions are going to train the model to detect TB in a chest X-ray. So it's really explainable when there is some audit, or if you need to explain it to your end users, you can always show the labeling functions and get them to agree or disagree whether that labeling functions make sense for this particular problem. So these kind of problems like medical image processing, like credit card or insurance, underwriting, those kind of heavily regulated industries, weak supervision is definitely a very big, is definitely very useful for those kind of industries.
So we have another question from Monica Khatkar, and she is interested in knowing what is the difference between normalization and regularization.
Okay, the regularization that I spoke about here is primarily to reduce what is called as model overconfidence. So when I say overconfidence, I mean when the model is wrong, but it has a high, it gives out a high probability in its predictions. So when a model is wrong, the probability of the prediction should also be low. That is the correct way. That indicates that the model is unsure of its predictions. But when the model is wrong, but it still gives a high probability of prediction, it means that the model is overconfident. Like it's wrong, but it is very confident. So it's overconfident. The goal of regularization is to reduce this kind of an overconfidence. We don't want the model to be so confident when it's making wrong predictions. So that is where the regularization loss comes from. I'm not sure, uh, like normalization is a typically is a different concept altogether. Like if you're trying to normalize a vector to like make it unit variance and so on. So like I wouldn't get confused between normalization and regularization. So regularization is just to reduce the overconfidence that the model has when it's making wrong predictions.
So we have another question. Can you please give your expert comment on means unsupervised and supervised NLP approaches, basically applied to NLP only?
Right. So NLP is a very large topic, right? So uh, recently there has been a lot of work in self-supervised, rather self-supervised NLP techniques. So it's a little bit different from the talk that we're having right now. Weak supervision is primarily focused on supervised NLP, right? So we want to fine tune a model based on labels that we are generating using these weak supervision approaches. Unsupervised, or rather semi-supervised, is one component of the cosine model. In the cosine model, we have a loss function that is the contrastive loss. Contrastive loss is something that is popular in self-supervised learning, but it is just one small part of the weak supervision approach. Right? The weak supervision has so many other things. We have the label model. We have cosine itself has like 4 or 5 steps involved. So primarily weak supervision is focused on supervised NLP approaches. It's not really focused on unsupervised.
So Miss Monica is again interested in knowing about entropy.
Okay, sorry, unfortunately, I'm not very familiar with entropy. Yeah.
Yeah. So we have another question from Mr. Bharani Dharan. That what is the difference between a strong AI and weak AI?
Okay, this is a very philosophical topic.
Okay.
So, like, uh, when we talk about, like, if you look at AI, the way it is depicted in the movies like Terminator, what's the other one?
All the movies from Avengers.
All the Avengers like Vision, all these like Jarvis, those are all strong AI, right? But our current technology is not yet at that level. Like recently, one of the Google researcher made a claim that one of Google's model is sentient. So that claim suggests that the AI is strong AI already, but I think we need to be skeptical of those kind of claims. A lot of what we are doing is perfectly explainable by mathematics, is a series of mathematical operations, is matrix multiplication, is non-linear activation functions. So like any claim that we have achieved strong AI, like for me personally, I'm very skeptical about it, but it need not hinder our use of the AI technologies out there. All the AI technologies that we have right now are still weak AI. They can solve one specific task, but they can solve that specific task like really well, even better than a normal human being, a median human being can solve it. Like one of the best example is all those ResNet and EfficientNet models. They can identify the objects and images at a level that is better than 97% of human beings. But that is still a weak AI, right? It is still, you cannot use that model to solve any other problems. So in terms of strong AI versus weak AI, everything that we have right now is still weak AI, but it is sufficient to solve our problems. It is sufficient to uh, create billions of dollars of job opportunities and yeah, basically help the economy tremendously. So yeah, I think be very skeptical if somebody claims to have achieved strong AI.
Yeah. Yeah, thank you so much, sir. And this is a very general question which I'm going to ask you now. Suppose that if any of our participants wants to collaborate with you in future, so first of all, what is the eligibility criteria for that, and what are the collaboration opportunities that you can extend to our participants?
Um, I do not have a ready-made answer for that, unfortunately. Like if anyone is interested, maybe ping me on LinkedIn, and yeah, we can discuss from there and see like what's the best way to collaborate.
Okay. So thank you so much, sir. Your talk was so informative for us. You have made this week supervision so easy for us to understand for all of us. And thank you once again for sharing your expertise on this week supervision. And you have shared so many resources with us that if anyone is interested in going into the depth of the week supervision, then he can or he or she can read that book also, which you have mentioned from the published by Orally. And you have also given us the links to so many resources. I'm sure that all the participants would have been definitely benefited from by attending this session today. Thank you once again, sir. Thank you so much
Thank you,
for
Dr.
sparing
Arun.
your valuable time.
Thank you, everyone.
Yeah, thank you so much, sir. And to the participants, we are going to share the feedback link. I think Dr. Gaurav has already shared the feedback link, which you can access from the chat window. And today's second session will be at 2 p.m., 2 to 3:30 p.m. So hope you will join us in time so that because we are in the habit of starting the session in time and finishing in time. So thank you all the participants for your patient listening and thank you once again, sir. Have a nice day, sir. Yeah. Bye bye, sir.
Thanks. Bye.
Yeah. Bye.